You walk into a dark room, you reach out, flick a switch, and instantly the whole space is just flooded with light.
Right. It's probably the most ordinary action in the world. We do it every day.
We do, but if you stop and think about it for just a second, I mean, what physically just happened?
It's a lot more chaotic than just a bulb turning on.
Exactly. So today we're taking a deep dive into this, answering that exact question. We're unpacking a really fascinating 15-slide presentation called The Mechanics of Light, a visual laboratory on the nature, propagation, and mathematical behavior of photons.
It's an incredible breakdown. We're going to get into exactly how light particles travel, the math behind their behavior, and where these principles show up in real-world uses all around you.
Yeah, so looking at slide one, which really sets the stage here, I just have to say, okay, let's unpack this. We flick a switch and there's light, but what is actually moving across the room?
Well, to truly understand what fills a room when you turn on a lamp, you have to kind of strip away the idea of light as just being on or off. You have to look at it a physical traveler on a journey. It has a specific speed, a shape, and very strict rules.
And it seems like the first rule is that we are just completely oblivious to most of it. If we're moving to slide two, looking at the visible spectrum and spatial propagation, the main takeaway for me was how blind human beings actually are.
Oh, absolutely. I mean, when we casually say the word light, we are almost always talking about the visible spectrum.
Which is tiny.
Right. It's a microscopic sliver of wavelengths. We're talking just 380 nanometers to 740 nanometers. But light is electromagnetic radiation, and the full spectrum is just massive.
The slide maps this out perfectly. On the far end, you have radio waves.
Right.
And then microwaves, which is literally the exact real world use of what you use to heat up your lunch.
Yeah, and then you get infrared, like those glowing heaters you see at outdoor cafes.
Exactly. And only then do we get our tiny little visible band of colors. And beyond that, ultraviolet, X-rays that doctors use to look at your bones, and finally gamma rays.
And the wild thing you have to remember here is that they are all exactly the same thing. They are just different forms of light.
Mind-blowing. And in a vacuum, every single one of them is tearing through space at the exact same speed, 3 times 10 to the 8th meters per second.
Which is roughly 186,000 miles per second.
But how it physically moves is kind of strange. The visualization here shows light radiating in expanding spherical waves. Kind of like I'm picturing dropping a pebble into a pond, but instead of flat ripples, it's this expanding 3D sphere.
That is the physical reality, yeah. But doing practical math with expanding 3D spheres is just an absolute nightmare.
I bet.
So for geometric optics, the presentation introduces the ray model. We basically draw imaginary straight arrows pointing in the exact direction the wave is traveling.
Wait, I have to push back on that. Why use imaginary straight arrows if the reality is a giant sphere? Isn't that just, I don't know, faking the physics to make the math easier?
Well, think about standing on Earth, right? The Earth is a giant sphere, but locally, where you are standing, it looks flat.
Okay, sure.
The ray model is a localized abstraction. If you look at a tiny enough section of that massive light sphere, the leading edge essentially flattens out, so its energy vector is moving in a straight line.
Ah, okay.
Tracking that straight directional arrow lets us calculate the exact path without getting bogged down in the full geometry of the sphere.
Localized abstraction.
Mm.
Okay, I can buy that. But if you think mapping a sphere is complicated, let's talk about what light actually is. Because moving to slide 3, we hit the wave-particle duality.
Yes. What's fascinating here is that light absolutely refuses to be categorized as just one thing.
It's the ultimate paradox.
For centuries, physicists were completely deadlocked. Is light a continuous wave or is it a discrete particle? And the universe's answer, which this slide shows brilliantly, is simply yes.
It's both. So the visual breaks this into 2 natures. First, the wave nature. You have a double slit setup. You shine light through a barrier with 2 little slits. And on the wall behind it, you don't get 2 illuminated lines. You get this overlapping zebra stripe pattern of interference. It looks exactly like water waves crashing into each other.
Yeah, they amplify in some spots and cancel out in others. That interference is undeniable proof that light is propagating as a continuous wave.
Because solid particles wouldn't make zebra stripes. They just clump up behind the slits.
Exactly. But then you look at the other side of the slide, exploring the particle nature.
This shows electromagnetic radiation hitting a metal plate. And it turns out discrete physical units of light photons, are literally colliding with electrons in the metal and physically knocking them out of place.
Right. They call those ejected particles photoelectrons. This is the photoelectric effect.
So a wave couldn't do that.
No, a continuous wave couldn't eject an electron like that. Ejecting a particle requires a physical billiard ball style collision. Only a discrete unit could knock an electron out of orbit.
So it travels as a wave, but the moment it hits matter, it acts like a discrete physical particle. That is just wow. So where does this impossible wave-particle hybrid actually come from? If we're moving to slide 4, we get to the genesis of photons.
Yeah, this maps out natural versus artificial light creation. The graphic compares the sun with an everyday LED.
So for the sun, it uses nuclear fusion. The diagram shows hydrogen atoms being smashed together under just immense pressure to form helium.
Right, and in that incredibly violent process, a massive amount of energy is released, and that eventually reaches us as a photon.
Just raw, chaotic power.
Yeah.
But then you compare that to the LED, the light-emitting diode, which uses electroluminescence.
It's completely different. It's this highly controlled, elegant quantum process. An electric current passes through a semiconducting diode.
Okay.
And as electrons move across the junction between different materials, they are physically forced to drop into a lower energy state.
And that missing energy has to go somewhere.
Right. It doesn't vanish. It is cleanly emitted as a single photon.
And the real-world use case here is huge. The slide notes that by 2030, LEDs are estimated to capture 80% of the entire lighting market.
Because of that technological efficiency.
Right, we aren't wasting power generating heat like with old incandescent bulbs.
Mhm.
We're just neatly dropping electrons down a step and popping out light.
It's everyday engineering harnessing quantum mechanics.
So we know how it's born and we know how it travels. But what happens when it hits a solid wall? That brings us, moving to slide 5, to reflection mechanics at a plane boundary.
This is the physics of the mirror you look into every single morning. The fundamental rule is a law of reflection. The angle of incidence strictly equals the angle of reflection.
Meaning if it hits at a 30-degree angle, it bounces off at exactly a 30-degree angle.
Exactly, it has no choice.
But the math here introduces sign conventions that I really struggled with. It says the object distance, as grain lies, is positive. But the image distance, brand prime, is negative if it forms on the opposite side.
Yeah.
And magnification is exactly 1. Wait, how can a distance be negative? If the image is supposedly inside the mirror, it's not physically there.
Mm-hmm.
I can't walk negative 5 feet into my bathroom wall.
And that right there is exactly why the math requires a negative sign. The slide calls this a virtual image.
A virtual image.
Yes, when light rays bounce off the mirror and enter your eye, your brain intrinsically expects that light traveled in a straight line. So your visual cortex traces those diverging rays backward, projecting them literally through the solid wall to a point of intersection that doesn't actually exist in reality.
So my brain is essentially hallucinating a room behind the mirror.
Precisely. The negative distance mathematically represents that the focal point is on the opposite side of the reflective boundary. It exists entirely in a virtual space constructed by your perception.
That is wild. And the magnification is 1 because it looks like the exact same size, just flipped into that negative space.
Exactly.
Let's put some numbers to this optical hallucination. Moving to slide 6, we have lab 1. Calculating plane mirror distances. So the setup places you 10 feet in front of a plane mirror.
Okay, so the core equation balances the real distance against the virtual distance to equal 0.
So if my real distance is a positive 10 feet, the equation dictates the image distance must be a negative 10 feet.
Right, meaning the total spatial distance between you in the real world and your virtual reflection in the mirror world is 20 feet.
Because the intersection forms on the opposite side. And this real-world application is why putting a huge mirror in a tiny apartment makes it feel twice as large, right?
Yes. Your eyes are literally focusing on a point 20 feet away, even if the physical wall is only 10 feet in front of you.
You're hacking your visual cortex.
Okay.
Okay, so bouncing creates virtual space. But what about when light doesn't bounce, but actually penetrates a surface? Moving to slide 7, we look at refraction mechanics and Snell's law.
So refraction is the bending of light when it strikes a transparent surface, like a glass window or a pool of water. It doesn't pass straight through, its path physically pivots.
And it pivots because its speed changes, right?
Exactly. The presentation introduces the index of refraction, labeled n. It's a simple ratio comparing the speed of light in a perfect vacuum to its speed in that specific medium.
Right, so N equals C divided by V.
Yes, and this is the foundation of Snell's law. It dictates the exact relationship between the angle the light comes in at and the new angle it takes when it crosses that boundary.
Well, let's see this in action. Moving to slide 8, we have Lab 2, deriving angles and speeds. The real-world setup here is a laser entering a solid block of glass from the surrounding air at a 60-degree angle.
Okay, so air has an index of exactly 1.00. The glass has an index of 1.51. By applying Snell's law, we can calculate the exact trajectory.
And the math shows the angle of refraction bends drastically down to about 35 degrees. So it came in at a wide 60 and snapped into a tighter 35.
And it slows down too.
Yeah, the slide says the laser slows from 3 times 10 to the 8th meters per second down to roughly 1.98 times 10 to the 8th.
Right. The light is basically hitting a physical speed bump. Because the atomic structure of the glass is denser, the wave is impeded.
Oh, I get it. It's kind of like driving a car fast down a road and your right tires suddenly veer off into thick mud.
That's a great analogy.
The right side of the car slows down instantly, but the left side is still moving fast, which wrenches the whole car into a sharp turn. The light turns because part of the wave hits the dense glass first.
And optical engineers take this turning mechanism to incredible mathematical extremes.
Oh, yeah, because moving to slide 9, we're looking at complex refractive geometries, and the math gets intense. The scenario asks for the exact angle of incidence for glass, where the refracted angle is exactly half the incident angle.
Right, finding a precise fractional bend like that requires substituting some heavy trigonometric half-angle identities.
The slide shows the algebra, and it proved the incoming angle has to be exactly, well, approximately 73.7 degrees to get that perfect split.
Huh.
But why do we care about mapping this with such intense trigonometry?
Well, if we connect this to the bigger picture, this precise trigonometric math is exactly how optical engineers design everything in our modern world.
Like what?
Think about prescription eyeglasses or the multi-lens camera on your smartphone. They use these complex geometric identities to ensure light bends at the exact fraction of a degree necessary to perfectly focus an image onto your retina or a digital sensor.
So they're literally mathematically corralling the light.
Yes, exactly.
Well, I want to see what happens when we push that to the limit. Moving to slide 10, this is total internal reflection. And here's where it gets really interesting.
It does. We just talked about light bending when it moves from thin air into thick glass. But the physics gets super weird when light goes the other direction, from a denser medium like water trying to escape out into a lighter medium like air.
The visual for this is crazy. It shows a flashlight shining up from underwater, and as you increase the angle of the flashlight, the refracted light bending out into the air gets wider and wider, leaning closer to the surface.
Right. And eventually, that escaping ray flattens out completely against the water's surface. It hits exactly 90 degrees.
And the slide calls that the critical angle.
Yes. If your light source tilts even a fraction of a degree past that critical angle, the light can no longer penetrate the boundary. It reflects completely back inside the denser medium.
Total internal reflection. It effectively turns the surface of the water into a flawless, impenetrable mirror from the inside.
Exactly.
Moving to slide 11, Lab 3 calculates this. Imagine a glowing point of light sitting zero point 0.3 meters below the surface of a pond.
Because of the critical angle, which for water to air is roughly 48.75 degrees, the light can only escape through a specific upward-facing cone.
And we can calculate the size of this cone. The slide takes the tangent of that 48.75 degree angle, multiplies it by the 0.3 meter depth, and gives us a radius of about 0.342 meters.
Visually, this means if you were floating above this pond at night, you wouldn't see a giant glowing body of water. You would look down and see a perfectly sharp, mathematically precise circle of light on the surface.
Just a glowing geometric portal in the water, and outside that specific circle.
The water's surface acts as a total mirror, trapping all the remaining light below.
Incredible. Well, speaking of visuals, let's shift to how we actually perceive color. Moving to slide 12, we tackle dispersion. It's the classic real-world example. White light passing through a prism and fanning out into a rainbow.
Right, because white light isn't a singular color, it's a superposition, basically a messy blending of all those different visible wavelengths we talked about on slide 2.
And the presentation explains that when this white light enters a new medium, its frequency stays constant, but its wavelength changes based on the index of refraction.
But the part that blew my mind is that the index it actually varies slightly depending on the specific color of the light.
Yes, the physical structure of the glass doesn't treat all wavelengths equally. Red light interacts with the atoms slightly differently than violet light does, meaning they experience slightly different speeds.
So it's kind of like imagine runners hitting a muddy patch on a track.
Some runners are affected more by the mud and slow down at different rates, so suddenly this tightly packed group spreads out into a wide line.
That's a great way to picture it because they slow down at different rates, the beam spreads out, red light bends the least, and violet light bends the most, creating the visible spectrum.
It's just a phenomenal sorting of energy. Which brings us to our final concept. We've sorted colors, now we need to filter the waves. Moving to slide 13, we introduce polarization.
Right. We know light is an electromagnetic wave. The slide illustrates this in a 3D graph. You have an electric field oscillating up and down, and a magnetic field oscillating side to side, perpendicular to each other.
And unpolarized light, like from the sun, is just a chaotic mess of these waves oscillating in dozens of random orientations all at once.
But when you pass that chaotic light through a polarizing filter, which is our real world use case here, like polarizing sunglasses, it acts like a microscopic picket fence.
It eliminates all waves except the ones vibrating in a single specific geometric plane. It blocks the horizontal glare and only lets the vertical waves pass through.
Exactly. It strips away the chaos.
But how does this happen in nature without manufactured plastic? Moving to slide 14, we look at natural polarization.
Nature has its own invisible picket fences. The slide outlines atmospheric scattering. When unpolarized sunlight hits atoms in our atmosphere, the vibrating electrons radiate secondary waves that become partially polarized.
So you look at a blue sky, you're seeing geometrically filtered light.
Yes. And then there's Brewster's law. It states that when unpolarized light bounces off a surface, like water, if the reflected beam and the refracted beam penetrating the water are exactly 90 degrees apart, the reflected beam becomes perfectly 100% polarized
Why 90 degrees?
because of geometry. At exactly 90 degrees, the vibrating electrons in the water are oscillating directly in line with the reflected beam. A wave physically cannot travel in the exact direction it is vibrating, so it can emit that specific plane of light back at you.
It strips away all the other angles and leaves just one perfectly flat plane of polarized light. Wow.
Yeah.
And we can use this invisible geometry to solve mysteries. Moving to our final slide, slide 15, we have Lab 4, sourcing the booster angle.
Right, so we have sunlight reflecting off calm water, and the glare hitting our eyes is completely polarized.
By using the formula for Brewster's angle, taking the arctangent of the water's index divided by the air's index, we find the magic angle is roughly 53.06 degrees from the vertical normal line.
And from there, the math is simple. If the angle from the vertical is 53.06, you subtract that from 90 to find the angle with respect to the water's flat surface.
Which is 36.94 degrees, meaning just by observing polarized glare on a random puddle, we can mathematically prove the sun is sitting precisely 36.94 degrees above the horizon.
This raises an important question, though. How much of the world around us is heavily filtered by invisible geometries that we just take for granted when we put on our sunglasses on the beach?
It really makes you rethink the entire journey of a single photon. We've tracked this whole process today, from a photon being violently born in a fusion reaction on the sun or quietly inside an LED, traveling as this impossible wave-particle hybrid, bouncing off mirrors to create negative virtual space, bending through glass, and getting mathematically filtered by the sky.
It's an incredible journey.
So what does this all mean for you?
Mm-hmm.
It means every time you look at a rainbow or your reflection or a glaring puddle, you are witnessing incredibly complex mathematical geometry playing out in real time.
And I'd add one final thought to ponder. We just learned that the speed of light changes and its path bends depending on the medium it travels through, right? It slows down in glass or water.
Yeah.
Well, consider that absolutely all the visual information we have about the universe, every star, every galaxy travels to us as light. And deep space isn't an empty vacuum, it's filled with massive clouds of gas, dust, and dark matter. So, how might these cosmic speed bumps and invisible refractive lenses in deep space be tricking our eyes about exactly how old or where the stars really are? Are we seeing the universe as it physically is, or are we just looking at a distorted virtual image?
Now, that is a thought to keep you up tonight. Next time you walk into a dark room and reach for that switch, take a second to appreciate the mechanics of the universe you're about to unleash. Thank you so much for joining us on this deep dive. Keep questioning the world around you, and we will catch you next time.